I thought we should start out today by revisiting our little friend, the white-tailed deer. Deer are a menace in the garden, but they are very cute, so we tolerate them anyway. We're going to be finishing up our discussion of logistic growth in just a minute, and then we're going to extend it a bit further and talk about how we can use that same model with a bit of a modification to talk about competition between species. And then we will move on for the principal focus of today's lesson, which will be on age structure in populations. So let's start off where we ended up last time, deriving a formula for capital R, the reproductive factor. And we can do that in terms of a plain old linear equation with the slope of the line, using some simplifying assumptions, being R, the intrinsic rate of increase, divided by K, the carrying capacity of the habitat, times N, population size, and then to that we have to add the y-intercept. And in this case, we've determined graphically that our y-intercept is equal to 1 plus r. So now, if we want to calculate a change in population over time, dn over dt is the symbolic formula that we've used before, we subtract the number of individuals in the starting population from the number at some future time, which we can call n sub t. So dn over dt equals n sub t minus n. Now we can also express n sub t as the product of the reproductive factor r and the starting population n. And so we can say n sub t equals rn, and then we can substitute that into the formula just above it. And then we get dn over dt equals capital Rn minus n. Now with a little bit of factoring, we can take out the n and come up with n times r minus 1. The next step is to substitute the formula for capital R that we derived into this formula. And so this gives us dn over dt, change in numbers over time, minus n times a minus r over k, the slope of the line. Remember, it's negative because the line slopes downward, times n plus 1 plus lowercase r, intrinsic rate of increase, minus 1. Then all we have to do is do some combining of terms, and we get dn over dt equals capital N times minus rn over k plus r. And then if we just rearrange and do some factoring, we come up with our logistic growth formula. Now let's turn our attention to this little guy here. This is a kind of a toad that is found in northeastern North America. But it is not just any old toad. This particular species is called the Fowler's toad. And Fowler's toad is interesting because it only occurs in certain kinds of situations. It tends to be found in areas that are underlain with sandy, gravelly soil. So we find it in eastern Connecticut and Rhode Island and eastern Massachusetts pretty regularly when the soil is right. But in many other areas in this region of southern New England, for example, you don't find it at all. We find its very close relative, the American toad, present. And so we have these very, very similar species with a very similar lifestyle and yet each occurs in a distinctly different kind of a habitat. This one in sandy gravelly soil, and the other species in other kinds of soil types that are more widespread across southern New England. So we can say that these two species that are otherwise so similar avoid coming into competition by being habitat specialists. So they subdivide their environment based on soil. Now let's take a look at a related but different example. We're now looking at an early spring garden, a late March garden in southern New England again. Notice all those little blue flowers. That is a garden plant called scilla, which is an old-fashioned kind of a thing that lots of older gardens around this region have planted in them. They do tend to spread pretty readily, so you notice that there's hundreds and hundreds of them here. So they've been in this garden for the better part of a century, most likely. So scilla is a kind of a plant that comes out in the extremely early spring, grows and flowers before anything else has even started stirring. It is one of those kinds of plants which as a group are referred to by botanists as spring geophytes, which essentially means that they come up early in the spring before leaves on trees come out and all that. And so you have this whole host of species that are adapted to do that. Things like daffodils do that, and crocuses, and a whole variety of different kinds of garden plants. But a number of wild plants do that as well. We have quite a few spring wildflowers here in southern New England that come out long before the flowers on the trees do. Things like bloodroot and a whole number of other kinds of things. Different lily relatives, stuff like that, all come out very early. And so again, what's going on here is these kinds of species, these spring geophytes, are carrying on their reproductive cycle in the absence of competition from trees and other kinds of plants that shed lots of shade on the forest floor. So it's another kind of a way of avoiding competition. And they do this subdividing by means of being specialized. So what I'm building up to here is the topic of competitive exclusion. This idea that when species are very similar, and if they're occupying the same habitat, they're going to be in intense competition for available resources. If the competition becomes intensive enough, what we might hypothesize is that one species might actually exclude another from an area. And in fact, that notion was quite a long time ago formalized by an individual by the name of Gauss into the competitive exclusion principle, which essentially states that no two species can occupy the same niche. This principle was developed into a mathematical model by two other theoreticians by the name of Lotka and Volterra. And basically what they did was to take the logistic growth model and add an additional term to it, which took into account interactions between two species. And so it appears as you see on this image here, with change in numbers over time, dn over dt, equal to r, lowercase r, times n, so intrinsic rate of increase times population size. So up to this point we're still looking at an exponential formula. And then we add in our logistic term, except that in this case we take into account the interaction of two species, species 1 and species 2. So N1 refers to populations of species 1, N2 refers to populations of species 2. And then this other term, alpha sub 1, 2, represents the effects of species 2 on species 1. In this term, this alpha term, is generally called the competition coefficient. In practice, figuring out what the competition coefficient is can be difficult. Designing a field study to measure that can be rather challenging. Now, of course, however, as has been the case with all these models we've been looking at, there are a number of simplifying assumptions here, some of which we've discussed already. And so this competition equation does not necessarily represent the way things really are in nature, but it gives us a first approximation under simplified situations, which allows us to gain a deeper understanding of how it is that species can, and in fact do, interact in nature. Now let's turn our attention to age classes of species. What we're looking at here is a summer adult herring gull, one of the common species of gull that you see along the east coast and even inland at lakes and garbage dumps and places like that. Notice how snow white his head is, and how snow white his breast is, and how the wings are pretty much uniformly slate gray, and then they have these black tips on them. Let's compare this with another individual. This is actually a different species. See how he's got this little black ring around his beak, and also, unlike the last bird that had pink legs, this one has yellow legs. This is a smaller species called the ring-billed gull, also very common on the east coast of North America. But both these species have a pattern of plumage, colors of their feathers in other words, that are rather similar. So notice this one has these little grayish kind of flecks on his head and onto his neck. This is the kind of pattern you see with adult birds again, but winter adults. So we see a difference between summer and winter. And in fact, we also see differences between adult birds and birds in their first 3 years of life. So first year birds are mostly mottled kind of brown, kind of ratty looking things. Second year birds less so, and third year birds less so yet. And then finally you get these nice neat white and gray birds with these black wingtips as adults. So we have 4 quite recognizable age classes in many of our species of gulls. This, of course, is the North American bald eagle, and it has a pattern of plumages rather like the gulls, in that this nice neat white head and black body and white tail that you really can't quite see in this photograph. Birds don't get those until they are 4 years old. And birds during the first 3 years of life are also recognizably different. In the case of a first-year eagle, they tend to be rather chocolate brown. And then second and third year birds have got quite a bit of mottling of brown and white on them. And then as they come into their adult plumage, that goes away and you get this look here. So in this and in a number of other species, you see recognizable age classes. And that brings up the issue of population structure. So let's take a look at that in some more detail. So we can define age structure like this. number of individuals in each of a population's age classes. And age classes in long-lived species are generally years. So we have 1-year-olds and 2-year-olds and so on. And that would be the case with things like gulls and eagles. And we can even recognize age classes in something like a salamander, like you see here. In eastern North America, we have the red-spotted newt, which has distinctly different age classes. We have the juveniles, like you see in the lower left, that are orange. And actually the large individual you see in this picture is one that's in transition between the juvenile stage and the adult. Newts do things kind of backward from the way that many amphibians do. In this case, the juvenile is a terrestrial animal, but the adult, which develops a rather considerable fin on its tail, becomes aquatic. So this kind of yellow tan individual that you see there has assumed more or less the adult colors, but it has not completely metamorphosed into that aquatic adult yet. Now, we could even talk about kinds of animals that have age classes that might be measured in days or weeks. So we could think of a lot of insects that do things like that. So in any event, once you have information on age classes, the structure of the population, then you can start making predictions about how the population will grow over time. Let's take a look at some graphics that gives us some insights into this idea. Here are some graphs that I've made that model typical kinds of age structures of populations that are undergoing different kinds of growth patterns. So if we look at that red graph on the left, that's a graph of a population that is rapidly growing. So for example, if we have a population of cottontail rabbits that have recently colonized some new area, they might produce an age structure pattern that looks like that. In human populations, we see age structure patterns like that in developing parts of the world, like in places in sub-Saharan Africa, for example. There's the base of the graph, which is represented by the earliest age classes, the children, and in the middle part of the graph, which is middle-aged individuals, and then the upper part of the graph, which are the senior members of the population. Now, if we look at the middle purple graph, that's a situation where you have a population undergoing modest amounts of growth. Like, for example, you might see in North America, in the USA and Canada, where we have quite a few children, in large part, however, because of immigration into our countries from elsewhere. So we do tend to have lots of children coming in and being born here to immigrant parents. And then we have a pretty good sized middle-aged group, and we have also a class of individuals who we might refer to as seniors. Now, in the graph all the way on the right, that blue graph, that is a situation where populations are pretty much stable over time. And many kinds of wild animal populations would be more or less like that. They might fluctuate from year to year, but more or less they don't really grow or shrink that much. It is also the kind of situation that you see in places in Western Europe where populations are not changing much over time. Places like Italy, for example. So what you have here are about the same number of individuals in all the age classes. Now, of course, the very senior individuals, you start getting people who are dying of old age, and so that one starts to shrink a bit. But there are not that many more children in the population than there are mature adults. Now let's turn our attention to the topic of survivorship. Let's look at this little guy here. This is a gray tree frog, another widespread species in northeastern North America. It is one that, like many of its relatives, lays large numbers of eggs in the springtime in ponds, and then these eggs hatch and produce tadpoles which swim around in the ponds for some time until they metamorphose into adults and then emerge from the ponds. However, in the process of going through these age classes, most of those eggs and tadpoles wind up getting eaten, so that the probability of survival at these early age classes is rather low. And so relatively few make it to adulthood, but then once they reach adulthood, they might live for a while. Now here's a bit different kind of a situation. This is a baby groundhog. Groundhogs don't have nearly as many young as frogs do, but they still produce a pretty good sized batch of young. But again, they are subjected to pretty heavy predation by owls and foxes and a whole host of different kinds of predatory animals. And so the survivorship of any one young groundhog is somewhat limited, at least, although because groundhogs have parental care, unlike frogs that do not, the survivorship of the young is still significantly higher. Now this little guy here was actually orphaned, and so when he was just a little peanut, a little sausage-sized thing, I raised him, and you can see he got quite used to taking his own bottle after a while. Now another thing about groundhogs, though, is that they are surprisingly short-lived. We kept this little guy. He became our pet. We never released him back into the wild, but at age 3 he died of old age. So they are rather short-lived, as even medium-sized mammals go. He was a rather short-lived one, and that's not unusual for groundhogs to be that short-lived. But while we had him, he was an extremely entertaining pet. They are more or less housebroken by nature. He kept his own little bathroom inside of his house where he lived and never made a mess in the house. And he was also very social. Groundhogs are moderately social kinds of animals. Not as social as their cousins that live in the prairies, the prairie dogs, but they are rather social. So this individual here would react to me just like he would to a parent. He would jump up and down when he would see me, and he'd climb up me and sit on my shoulder and groom me. He would just love to groom me. He'd sit on my shoulder and go through all my hair. So he was a very interesting kind of a little creature to have as a pet. But again, in nature, groundhogs do tend to suffer pretty substantial mortality from predators. Now here's another slightly different kind of a situation. These are again captive, domesticated animals. These are chicks. And so being in captivity, they are not subjected to predation, so their survivorship does tend to be pretty high, unlike their wild cousins. Now birds, like things like groundhogs, do engage in parental care, which means that the probability of survivorship of their young does go up. But what you tend to see in wild bird populations is that there's a pretty steady mortality over time. So although you don't have steep mortality of the young, individuals are turning over in a population throughout the age classes. So you have a rather steady decline in numbers of individuals within age classes. And then, of course, you have animals like these. This is the human in his natural habitat. And humans also have parental care, but much more extended parental care than do birds or groundhogs. And creatures like humans tend to have very high survivorship of juveniles and early age classes, and you really don't see a whole lot of mortality until old age in humans. And so it's a very different pattern of survivorship than you see in lots of other kinds of animal species. So here's what I'm getting at. There are three general kinds of patterns of survivorship that we see in nature among age classes of individuals. So if we look at the blue curve on this graph, that's representative of what we can call type 1 survivorship, typical of humans, where you have high survivorship of early and middle age classes, and you don't really see a lot of mortality until old age. Now in the straight line graph that you see here, that straight line going downward, that would be a type 2 survivorship curve, where you tend to have rather uniform survivorship of all the age classes. And this is what you typically see in animals like birds. Groundhogs may not be too much different from a curve like this, by the way. And then the red graph, the lowermost one, would be a type 3 kind of survivorship curve, typical of things like frogs and lots of kinds of insects, for example, where you have very high mortality of the early age classes, and then if individuals get past a certain point, then they do tend to live for a while. The last thing that I'm going to do today is introduce the concept of the life table. Life tables are mechanisms for calculating survivorship of age classes in populations. So we can use them to look at things like population change over time. So to compute population change, we need information on survivorship of different age classes and fecundity, which is another way of saying birth rate within age classes. So we have to gather information like that. Life tables are used a lot by things like insurance companies to calculate risk. But they're also used by population biologists to learn about how it is that we might project population growth or decline over time. And of course, when we're talking about age classes, it does depend upon what kind of creature we're talking about. So with things like humans and snapping turtles that live a long time, then we're using age classes of years. But how about like this little guy in the upper right hand corner of this picture, the meadow jumping mouse? Mice often don't even live a year. And so for an organism like that, that starts reproducing when it's only a few months old, then months are likely to be a more usable age class. So before we actually get into the mechanism of calculating in life tables, I think we should wait till next time. So we will end on this note for today, and we'll pick up with how to calculate next time.